Today we're taking a look at solving factorable polynomial inequalities algebraically. In the previous lesson we used the graphing calculator to help us solve questions. In this lesson we're going to use some of our skills like factor theorem, synthetic division to help us solve these word problems. We're going to take a look at this question later on. It involves the excavation of a swimming pool and trying to determine the possible dimensions based on some set criteria. But before we get to that, let's take a look at solving questions that we've attempted before. The instructions are to solve each inequality. We are asked to find out when this quadratic is greater than or equal to 0. There's a number of different ways that we can solve this, and one method we're going to look at is identifying the x-intercepts. If we write out the x-intercepts, x equals -3 and 2x minus 3 equals 0, 2x is equal to 3, and finally x is equal to 3 over 2, we have identified the 2x-intercept. Once we've determined the x-intercepts, we can use a process known as the interval method or interval technique to help us to solve the inequality. And how we do it is we draw a horizontal line and we label on it our two, in this case 2x-intercept, -3 and 3 over 2. We then draw interval lines at each of the x-intercepts, and these don't have to be perfect. And what we want to do is we want to use test points, and we're going to test points on either side of -3. So the first test point I'm going to use is -4. Now I can use -5, -729, but -4 is the next lowest number, and I want to use small numbers to make the math a little bit easier. And what I do is I substitute in a -4 wherever there was an x, and I ultimately solve the inequality. Oops, that should be -4. And so what I do is I take a test point of -4 and I substitute it into the factored form. Now it's important that this is factored because it makes our math a little bit easier, as you'll see in a few minutes. So we plug in 2 times -4, subtract 3, and we simplify these. -4 plus 3 is -1. 2 times -4 is -8 subtract 3 is -11, and when I multiply these together we end up with +11. Look at the inequality sign and ask yourself, is 11 greater than 0? Is that a true statement? Yes, it is. So this is going to be part of our answer, our solution. So from -infinity up to -3, but not including -3. Then we want to pick another test point in the next interval. So because the number 0 exists between -3 and 3 over 2, I suggest you use that. It just makes the math a little bit easier. Now in this case, I'm actually not going to solve in finding the number because I'm not even concerned that this is an 11. All I'm concerned about is it's a positive number. So in this example, I'm going to instead, when I take a look at x plus 3 and 2x minus 3, I'm just going to plug a 0 in here and a 0 in here. Well, ultimately the first bracket becomes a positive number and the second bracket becomes a negative number. And so in this particular case, I'm going to multiply a positive times a negative to get a negative and ask myself the same question: are negative numbers greater than 0? The answer is no, so this is not part of my solution. And I repeat. So I'm at 1.5. My third test point to the right of 1.5, I'm going to use 2. Again, when I substitute a 2 in, this is 2 plus 3, which is 5. I'm not concerned about the 5, just the fact that it's positive. And 2 times 2 is 4, so it's like 4 minus 3, which is also a positive number. A positive times a positive is still a positive, and positive numbers are in fact greater than 0. So I do have 2 intervals where my answer is obtained or is correct, and the first is going to be, let me just erase this, the first is going to be from -infinity up to -3, but because of the inequality it's only greater than 0, I don't include my x-intercept of -3. And it also includes from 3 over 2 to +infinity, all round brackets. And it's always round brackets around infinity, but round brackets around the -3 and the 3 over 2 because it's just greater than. So that is a method of solving inequalities using what's called the interval method. And we can use that in many, many cases. So the solution is going to be here. Let's try that with a little bit more difficult question, this time involving a cubic. So our ultimate goal is to find the factored form of this equation. I assume, or I treat it as an equation or an equal sign, even though I know it's an inequality. And if this was an equation, then I would look at trying different ways of factoring this. And so I'd look for a common factor. And I notice that I can divide each of the numeric coefficients by 2. So the first thing I'm going to do is I'm going to factor out a -2. Now, this is a good question. I want you to remember that that's a -2 out in front. What's left over is x cubed plus 3x squared minus 6x minus 8. Now that I have that -2 factored out, I take a look, and because there's 4 terms here, I take a look at the possibility of grouping. I know I can factor an x squared out, and let's just try this to show, but I'm pretty sure it's not going to work. I can factor out an x squared, and I'm left with x plus 3, and in the back part I can factor out a -2, and I have 3x plus 4. Because these are not the same, there's no grouping that can take place. So let's get rid of that and start again. So we don't have any more common factors. We can't factor by grouping. We're now looking at factor theorem. And we would look at the factors of 8. So plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. I am going to settle on the fact that 2 will give me a 0. And you'll have to trust me or try it yourself, but if you plug in 2 for each of the x's, this polynomial will result in 0. That allows me to use synthetic division and determine what the quotient is going to be. Bring down the 1, 2 times 1 is 2, and add. 2 times 5 is 10, and add. 2 times 4 better be positive 8, and it is. That gives me the 0 I knew I was going to get, because here it is. And now I can write out my factors. So don't forget that -2 that we factored out. Don't forget the factor of x minus 2. And then you can write the quotient that we achieved down here as x squared plus 5x plus 4. And this is still an inequality, so I want to find out when all of this is less than 0. Looking at this quadratic, I want to see if I can factor it, and I believe that I can. The factors of x squared plus 5x plus 4 are x plus 4 and x plus 1. This is now in total factored form, and I can go back and I can use the interval technique now the same way to determine whether or not, or where this function is less than or equal to 0. My first one is at 2, then at -4, and at -1. I like drawing these dotted lines. They're not necessary, but it definitely shows me how many intervals and how many test points I'm going to need to use. And so in this particular case, I actually have 1, 2, 3, 4 intervals that I'm going to test for. So I'm going to start with -5 as a test point. Once again, pick a number to the left of -4. You can use bigger numbers if you want. But once again, we're looking at the factored form with the -2 in there. Quite often we forget that -2, but we need to include it. So looking just at the sign changes. So I have a negative out in front from the -2. If I take -5 and plug it in, -5 minus 2 is -7, but I don't care about the 7, I care that it's negative. Plug in -5 here. -5 plus 4 is -1, there's a negative sign. -5 plus 1 is negative. When I multiply these 4 negatives together, I get a positive. Are positive numbers less than or equal to 0? Well, that's not true. So from negative infinity to negative 4 is not part of my solution. Pick another number. I'm going to choose the number negative 2. Again, looking at the signs, there's always this negative sign out in front. Minus 2 more is minus 4. Minus 2 plus 4 is positive, and minus 2 plus 1 is negative. I'm going through this very quickly, but once again, it's just a repeating pattern. Negative times negative is positive, times positive is positive, times negative is negative. Are negative numbers less than or equal to 0? Yes, they are. I can use the 0 test point, so I continue to plug in negative, negative, positive, positive. That results in a positive, and are positive numbers less than or equal to 0? No, they are not. And you see the pattern happening now. I'm just repeating my steps over and over. A negative, a positive, a positive, a positive. That simplifies to be a negative, and yes, just like before, negative numbers are in fact equal to less than or equal to 0. So I have my answer occurring in between these two numbers, and from 2 continuing on to infinity. Now I have to be a little bit cautious here because I do have a less than or equal to sign, so there might be some square brackets that I'm dealing with. So my solution is negative 4 to negative 1 inclusive, meaning it does include those values, and then from 2, including 2, all the way to positive infinity. Now this interval method, the technique that we're using, works for any case of polynomials that can be factored. But you could also use a graphical approach. And what you can do with this is you can look back up at the original polynomial. This is a cubic equation with a leading coefficient that is negative. So once I have the x-intercepts, I can actually sketch this out. And what this looks like is, well, if it's a cubic equation with a negative leading coefficient, that means it starts high, travels up, and through. And looking at this line that has just been drawn, where is the line less than or equal to 0? Well, that's between these 2 points, and from 2 continuing on out to positive infinity. So a graphical approach will definitely work as well. You still have to go and find all the x-intercepts through all the factoring work that we've done.